In massive datasets, the primary challenge is the time required for data retrieval. When information is stored in a simple sequence, a computer must check every record one by one until it finds a match. A hash table is a data structure designed to bypass this sequential search. It uses unique keys to calculate a specific memory location, allowing the system to find data without looking through the rest of the collection. This mechanic is similar to a physical locker system. To retrieve an item from a locker, you don't start at the first door and open every one until you find your jacket. Because each locker has a unique number, you walk directly to that specific door. Hash tables apply this same logic to digital storage. This structure changes data retrieval from a process of scanning through an entire list into a system of direct addressing. Our first step is coding the hash function. This function performs the calculation that determines where each piece of data will be stored. To store the name Bob, our function looks up the Unicode numbers for each character, 66, 111, and 98. We add these for a sum of 275. We divide that sum by 10. The remainder, 5, becomes our hash code, acting as our storage index. On the storage side, we create a Python list with 10 empty elements. Each of these elements is a bucket, indexed from 0 to 9. The hash function assigns each name a destination. Bob goes to bucket 5, Pete calculates to 8, and Jones routes to 1. The code places these items directly into their calculated slots. By combining this mathematical conversion with a pre-allocated array, we create a system where the destination of the data is known before the storage process even begins. This setup works until two different inputs result in the same index. For example, we may have the name Lisa already at index 3 when we try to add the name Stuart. If the hash function for Stuart also returns a 3, we trigger a collision. This happens when math assigns two items to the same location. In a basic list, the new data overwrites the old. Stuart would occupy the slot, and Lisa would be lost from the system. To prevent this loss, we use a technique called chaining. We modify the structure of our buckets. Instead of holding a single value, each bucket in the array becomes its own nested empty list. Now we use the append function. When Stuart is assigned to bucket 3, the name is added to the list already containing Lisa, allowing both pieces of data to remain in the same index. Chaining ensures that even when mathematical overlaps occur, the integrity of the data is maintained as the table grows. This chart shows the mathematical advantage of the hash table using big O notation. While a standard array search time, or O of n, increases as the dataset grows, the hash table search time tracks as a flat line. This flat line is O of 1, or constant time. It means the time required to retrieve an item remains the same whether the table contains 10 items or 1 million. This efficiency is the reason hash tables are used for large-scale applications, including database indexing, rapid web caching, and password verification. Every millisecond, global data systems use these mathematical addresses to sort and retrieve millions of requests across server networks. Understanding the mechanics of a hash table provides a direct look into how modern software maintains performance at scale.